think this is working now, so hopefully we should be seeing this stream live. Very exciting. Oh, just want to make sure this is working. Okay. So I'll try to post the video of today onto our classroom. So if you want to watch us go through these, yeah, we're alive, okay. So if you want to watch us go through these questions again later, you can definitely look that up. Put this on, hopefully get a little bit more pickup on things. Also, I'm not sure if I'm getting, this is the microphone over here, so we just gotta check. Okay. Okay, hopefully it records the audio, otherwise it's not very much good, but that's always the question. Okay, so put the following in order of increasing energy: green light, X-rays, radio, red light, ultraviolet, microwaves, blue light, gamma rays. I noticed that for some of you, this is, or for all of you, you don't have color pictures like I do, so it's not quite as obvious. So it might be worth going in on this picture here and just putting a little reminder that it is red. You could go yellow. It's not a very good yellow, but that's okay. Green is another color in the middle. And then you have your blues and your violets. It's always easiest to remember that violet is the last one because it's ultraviolet is the next, is the one that causes cancer. So ultraviolet is the bad radiation. Infrared or red heat lamps, those are usually heat. Those are not too bad for you. You just get warmed up. They have, there's like red heat light lamps or infrared lamp places you can go and sit under a red light and be warm. And there's also places you can go for a tan, and those use ultraviolet light. And if you've ever been in a tanning bed, you know the light that comes out is kind of bluish. So, and that's because it's the high energy stuff. So high energy is blue, low energy is red, and green is right in between. So for our colors, that's where our colors are going to be. So we have green light, red light, blue light. Feels like a game I would play with my children. So we know that red light is going to be lower than green, which green is in between blue. Those are all visible, so that visible spectrum is right in the middle of our full spectrum. So now we just have to figure out the other 1, 2, 3, 4, 5, the other 5. We did just talk about blue and then violet, so what would be the next one after blue? Ultraviolet. Cannot help but think about that terrible movie, Ultraviolet. If you haven't seen it, don't. Not worth the time. Is that Mila Jovovich in that one? I think it's the Mila Jovovich one. It's the Aeon Flux came out like the same year, and that was also terrible. Anyways, so the future. I mean, it's terrible and kind of awesome, but it's terrible. Okay. Then we start looking at things that we have only a couple things left. We have microwaves, and we don't have ultraviolet anymore. We have X-rays and radio. So I remember back in the day, I used to have I think I had a little hand crank radio. You could crank it up by hand and you could get radio signals on it. So in a way, that's kind of an indicator that radios don't have much power in them. It doesn't require very much to power a radio or to collect radio waves. So radios are way down here. They are the lowest ones. They're very, very long. They're also they're the frequency we use to go over long distances. Our cell phones work in the microwave range. And that's one of the reasons that you need cell phone towers. You need so many more cell phone towers than you need radio towers. We could have one AM radio tower just in the middle of the city and it can produce enough sound you can pick up in the country, but we have multiple cell phone towers, yes.
Satellites that catches the cable or the internet.
Yeah, so I'm not sure what those would send down in. They probably are going to use in the microwave range too, is my guess. Yeah, like satellite radio and things like that. Yeah. I mean, I guess if it's satellite radio, it sounds like it's radio waves, but they might use more intensity too. So so microwave is where our cell phones work. They work in just the crossover between microwaves and radio waves, and that makes their distance they can travel without getting all scrambled much shorter than radio. Also, AM and FM. FM is higher frequency than AM, but the higher the frequency is, the more information you can put in. So with FM radio, you're allowed to have, you can actually put in enough information to include stereo sound. And AM radio is, the wavelengths are so long that you can't actually include as much information in that signal. And so AM radio will travel farther. So if you're a country kid, you might have grown up listening to AM radio. What is it, like 990 on for CBC? I think CBC is like 990. We used to always listen to AM for some reason, even though we live in the city. And then, but on FM, you can have stereo sound. So you'll find that all the music channels were on FM, and all the talk radio used to be on AM. And that was because talk radio, they didn't need stereo, they just needed mono sound, and FM radio needed the boost in signal. But FM radio could only reach the whole city, and even then, like, some of the stations aren't very crystal clear. If you ever listen to the University of Manitoba's radio station, you get like too far away from the university and it starts to really drop in terms of signal quality. Meanwhile, something like, whatever Power 97 is now, are they still Power 97? There's something else. 92, yeah, 92 City or whatever. Those stations they have enough money to spend money on powering their signal, and they're able to send that signal quite a ways. You can drive almost all the way to Ontario and still be listening to those stations. Okay, and then the last one is the mean one. That's the gamma rays. That makes Hulk mad. So that's where I always put it. It's the only one with enough power to turn Bruce Banner into the Hulk. It's not true, but it is. What's that? Oh, did I forget X-rays? Okay. Well, you don't want to get hit with that. You don't want to get hit with gamma rays. X-ray, the occasional X-ray is okay. So that's why I always put my X-rays in between, even if I forgot them. So thank you for catching that. X-ray. Yeah. So you can get your X-rays when you need them for your teeth or for your body. They are somewhat toxic to your body, but they aren't nearly as damaging as the gamma rays. Gamma rays you really don't want to play with if you can help it. All right. So how did you describe the relationship between frequency, wavelength, and energy? Anybody want to share?
Yeah, energy is directly proportional to the frequency, and frequency inversely proportional to the wavelength.
Great. Yeah. I love that. I'm just going to steal that right away. So Johanna said energy is directly proportional to frequency. It's Q, not a G. Not the frequency. Frequency and frequency. Frequency is inversely proportional to wavelength. Notice that we're using the term proportional. That does mean that there's something there. You still have to do a little bit of math to change between one and the other. They're not directly convertible, but they are very close. Or they change in an equal way. Okay, here's a tricky one. Why is light called electromagnetic radiation? I'll take anything simple. I don't want you to get too crazy.
Because it is made up of electric and dynamic.
That'd is made up of electric magnet. Yeah. I'm just gonna be hemming and hawing about the made up. Yeah, I think I can work with that. Yeah, I'm just going through my filter, make sure I'm not leading you in a misconception there. Yeah, so we can say that light has an electric component and it has a magnetic component, or it is composed of both an electric. Yeah, that's about it. Let's go with made. Yes, Nelly, what do you got?
Could we say that it just emits electrical magnetic fields?
Yeah, I think that's closer to what I'm thinking about too. Yeah,
Is that the book is
mathematically demonstrated. That does sound like me.
demonstrated?
Yeah, it's mathematically demonstrated. Yeah. Let's see. Yeah, so if we play around with our little definition we used earlier. Mathematically demonstrated that light was composed of both waves of electric and magnetic energy, or electromagnetic energy. Yeah, okay. So let's yeah. So I think we can work with all that. So it is light has both. It has is. I'm going to try to use both. I try to use your language if I can. So is made of both an electric and magnetic parts. And then let's go with Nellie's part here. So now it will be E affecting both the electric and magnetic fields, or emitting both electric and magnetic fields. Affecting is fine. It's more generic, I guess. Emitting of electric and magnetic fields, that also works. Disturbing electric and magnetic fields, if there's one that already exists. I really gotta stop being so obsessed with being right and not like lying. I spend way too much time hemming and hawing about what the right way to say something is. Probably should include the word perpendicular in there somewhere if you want. It's made of perpendicular electric and magnetic parts. So that's great. Great word in there. I'm tempted to edit, but I know that as soon as I edit, somebody goes like, "Oh, I just wrote that down." Okay. A mercury lamp emits radiation with a wavelength of blah. What is the energy of a photon from this mercury lamp, I assume, not just a random photon. So this is, of course, one of the equations. We want to look at our board here. We have two options. We have the E equals h nu, and we also have the E equals hc over lambda. Which one would be the more appropriate equation? This one? Alright, yes, the lambda equation is going to be the one we want to use. So let's write out what we have first. We've got a wavelength, so always try to use the unit that you're going to, the symbol that you're going to find in your equation sheet, because that'll help you find the right equation. Alright, call it 10 to the negative 7 meters. And they are interested in energy. So then I go to my equation sheet and I look for an equation that has both those letters, those symbols in it, and I do have one, and on my equation sheet it's even in the right order. I don't even have to do any modification. So that's always nice. It's right there, it's in the right order. I can see that I have a couple pieces I'm going to need. I'm going to need my H, which at some point you're probably going to memorize. 6.626 times 10 to the negative 34. And there's a whole bunch of units that I'll have to grab. Let me see if I can do it. It's meters, kilograms per second squared. Is it meters squared? I feel like it's meters squared. Is that right? Yeah.
kilograms per
Is it meters squared per kilograms? Is this correct or is there a change?
Yes, right.
Seconds doesn't have a scale.
Oh, seconds doesn't have the square. Okay, that makes sense. Okay. That would have been a joule otherwise, right? Okay, and then I have my C, which we are going to go. Are we doing 2.99? Sure. 2.9. Oh, I'm never going to remember that. Okay, let's go back up here. C that we're using is 2.9979. Boy, is that really close to 3. Three. I'm tired of writing numbers. 3.0 times 10 to the 8.
That was 6.63.
You could reduce it to 6.63, especially because you're only dealing with 3 significant figures in your initial number anyways. But it's always nice to have to use as many digits as you can. So with the C, I would have to go to, I was just looking at the C, and I have to go to 4 to 5 digits really before I start to before it's not 3. So that's where I was like, well, if you rounded up you could go, if you went 2.99 and then rounded, you'd actually round to 3, so it'd be 3.00. You could go 2.998, I suppose, so that would be the next option. So you could go 3.00 or 2.998. Considering our initial number has only 3 significant figures, we can safely use speed of light up to 3 significant figures as this unit.
Three
3 sig figs, yeah. Significant figures are, 1, 2, 3.
But still, this significant doesn't affect the calculation, right? Or just the proper way of writing.
What do you mean by that?
Like it is really 3.00, right? It's
Mhm.
360,
That's correct.
but it doesn't affect the calculation part.
Doesn't affect the calculation, no.
That's the right way of writing it.
Yes. Yeah, the zeros won't affect the actual number. I understand, yeah. But because we want to keep track of how much significance we have, we're going to use that. If we wanted to move up to 4 significant figures, we'd actually have to go to 2.998, because that would be the next rounding. And if we wanted to go to 5 significant figures, we would go 2.9979, and then might actually be 980. Oh no, 79. So you could actually go 5 significant figures would be 2.9979. I'm getting too lost in the woods here. I'm digging around in the weeds instead of focusing on the important part here. And I'm never going to get anything done if I keep digging. Okay, so we're going to take our 2 numbers, we're going to move them over into our equation, we're going to do our calculation, and some magic will happen, and we're going to get a number. So I'm going to just draw a really big line because I know I have this huge numbers to draw. I'm going to do some cheating that you can't do, but I have to talk, so it's okay. So I'm going to do that. I'm going to put a dot for multiply. I do sometimes use the dot for multiplying, especially if I'm multiplying 2 big numbers, and that way it just doesn't get confusing about we just said that I can use 3. If you ever want to check to make sure that your significance doesn't matter, you can feel free to do the equation again and see if it actually makes a difference, to do it with the different numbers. And then down here we're going to put our 4.36 times 10 to the negative 7 meters. Some things happen here. We can see that the meters would cancel out, but the seconds here are going to combine themselves. So we're going to end up with seconds squared as our answer. That's good because that gets us closer to our unit of joules that we want. Shrink it a little bit just so it fits better. And does anybody want to do that calculation for me? I see 10 to the 8 and 10 to the negative 7, so that's going to be a 15. So I'm adding a 15 to my 34. 34 minus 15 is going to be 19. So 10 to the 19. So I'm looking at something in the 10 to the 19s area. That's always a good check to check your. So what I'm doing here is I'm doing some basic math with just the 8s, the 7s, and the 34s, just to make sure that when I punch in my calculator, I didn't make a mistake. So negative 34 plus 8 is negative 16, and then, or negative 26, sorry, negative 26. Negative 26 minus negative 7, so add 7, would give me, negative 26 plus minus 7, so it's 19, right? So I end up with negative 19, so I'm hoping that when I punch in my calculator, I get negative 19 plus or minus 1, based on what happens with 3 times 6 divided by 4. You can, and estimation is always a useful technique for this sorts of calculations. This is, of course, if you're very mathy, and if you're not someone who does a lot of math, then this is probably not fun for you. So, could someone give me the answer though? 4.56, and that's times 10 to the negative 19. Okay. 19 joules. That's a joule. And then if you're really nice, you'll be copying and pasting that somewhere that I can find it, and putting some sort of indicator to say that this is the answer that you want me to correct.
So,
Yes.
if we use all the decimals,
Mm-hmm.
it makes error, becomes error in the answer.
It
So
becomes an
how
error?
many decimal points do we have to use?
So if you use more decimal points, you shouldn't get your number's just more accurate. So I will try to, if I'm marking something and I notice a difference in the decimal points that you use, I'll double check the calculation and make sure that it works out. As long as it works out that way, that's fine. So, do you want to show me the number you got, and then I'll just share? So to me, this looks fine. This number's probably okay. It just looks like there might be an error in the way the exponents were done.
So we have
Yeah, you just have to watch out how this multiplied.
yeah, we have to add and we'll subtract those.
If you did it in the calculator, it should just work out. So if you go 6.66, and this, negative 34. No problem. And then because the answer, if you do it with all the decimals, it's 4.555. Going down to two places after the decimal means that it was 5.5. That 5 is more than half, so we're going to go up to 6. Great? Great. Yes, Miss.
On exponent is the next answer.
Which one?
Like say 34 minus 8, 26 minus 26 negative.
Mm-hmm. Yeah, so it'd be negative
So-
26 and then minus negative 7.
Minus 26 minus 7 is
Yeah, so I think you're talking about the estimation?
yeah.
Yeah, so we're talking about negative 34 plus 8
Yeah.
and then minus negative 7. So it's a double negative because it's a division.
And then 26 again.
Yeah. So if you divide by negative 7, then by an exponent of negative 7, then you're actually doing a double negative, which means it's an addition. Which gives us negative 19. We can go over it later, just you come ask me, I'll show you. Okay. So this is gonna be just my thought bubble here. Okay. Calculate the energy and frequency of a red light with a wavelength of 6.45 times 10 to the negative 7 centimeters. I thought this was a particularly cruel question because they've mixed units and they put centimeters and scientific notation. Did anybody do the conversion to meters?
Yeah.
And what did you do to get the conversion to meters?
-7.
Yes, so we would go down by 2. That's correct. So we have to remind ourselves that a centimeter is 10 to the negative 2 meters. So we're going to end up doing our wavelength as 6.45. The number doesn't change, which is nice, which means that at the very least, if you just punched through and you did all your calculations, you're probably going to be okay in terms of getting the first part. You're just going to have a mix up in your tens, in your exponent powers. And then we have to go, we have sort of, I'm just going to do the work here, 10 to the negative 2 meters. That's sort of what they're actually asking for. And then here, this combination, these are the same base, different exponents, multiplication, so we add our exponents. That's how exponent rule works. Who would have thought you could not escape math coming to this class? Okay. So this would be 10 to the negative 7 meters. I love exponent rule. It's very fun. It's a great estimation tool. So if you're looking for more on this, we're talking about exponent rule, and that's a great place to go review. Check out a Khan Academy or something about exponent rule if this is something you don't remember how to do. In chemistry, it's relatively simple. We're usually only talking about the tens, or especially for scientific notation, we're really only talking about exponents of base 10. So hopefully a little bit of review in that, and it'll be a little bit easier to understand what we're trying to do. Okay, so they want both energy and they want the frequency this time. Aren't they greedy? So there's lots of options at this point in terms of what you want to do next. You can start with any of the equations we have, really, that have a wavelength in it. So we have this choice. We could use this equation here. We could also use this equation here, or this one particularly. Either way, we could get one of those two answers right away. So it's your choice. Do you want to convert to frequency first, or do you want to convert to energy first and then use your energy number to find your frequency? Or you could do both equations and then find both. Yeah, that's a great one. Yeah, there is also there's like a really pro tip is if you take your calculator, you can actually program Planck's constant into one of your pre-programmed numbers. So if you have like the ability to call up letters, there's actually a way to pre-program it in there, so you never have to type in 6.626 again. If anybody wants to know how to do that, I could probably figure that out. It's an option that you can do. You can even put C under. You can put your speed of light under your letter C. I think most of you are using a calculator very similar to the one I use, and that one can definitely pull that off. I've definitely those two calculators I've used before, and that's the Casio and the Sharp, and both of those are able to do it. There's usually little letters and an alpha button. So anyways, once you have the constants, it's really easy to play around with these sorts of things. So we can go that route. So let's convert to frequency by dividing C by lambda. If you chose to go a different route, then just hang tight. Let's just check our numbers at the end, and we won't because we're out of time. Almost had an end to the class. Okay, well, I'm just going to stop my stream. All right, so thank you, everybody. For tomorrow, I tried to build a fairly straightforward little quiz about all the stuff from lesson 0 and lesson 1. We will just try it. It's going to be multiple choice on the laptops. So I have it set up so that essentially it unlocks on our classroom at the time of our class. It can only be accessed through the through the Chromebooks in this that are Winnipeg School Division Chromebooks. So you do have to be on site to do the quiz. And yeah, we're just gonna try it. I have never done the quizzes this way, but we'll try it. Whether we use it towards your mark or not will probably depend on how we do. So if we go, if the average is over 80, I'm probably gonna use it. If the average is under 80, I'll use it as a piece of information about where we should go next. Okay? I'm hoping that it'll take half an hour, and then we can finish up these answers. Okay, so that's my goal. It's not supposed to be long. Okay, so thanks everybody. See you tomorrow. Thank you again for coming. Down. Thanks.
So we go over the rest of it tomorrow.
That's my goal. Yeah.
I just thought it was like, you know, do my own thing, right?
Yeah.
Right one after.
That's great. That's awesome. That's a perfect way to do it.